Approaching the exam effectively requires a strategic mindset. Firstly, tackle the easy questions first. This approach helps maximize your score, especially if you are short on time. It also reduces the impact of simple errors by allowing more focus later on challenging problems. Secondly, carefully read each question and fully understand what is being asked before attempting to solve it. Avoid immediately plugging in numbers without a clear strategy. This prevents wasted time and potential mistakes. Thirdly, utilize all available resources during the exam. This includes scrap paper for calculations, a calculator for complex computations, and any reference materials provided. Effective use of these tools can significantly improve your accuracy and efficiency. Fourthly, if you are unsure of an answer, make an educated guess. Since there is no penalty for guessing, it is better to attempt an answer than to leave it blank. This strategy increases your chances of earning points on questions you are uncertain about. Fifthly, avoid getting discouraged if you encounter a difficult question. Move on to the next question and return to the challenging one later if time permits. This prevents you from getting stuck and wasting valuable time on a single problem. Sixthly, maintain confidence in your abilities. Remember the time and effort you have invested in studying and preparing for the exam. Believe in your knowledge and skills. Seventhly, take a moment to relax and breathe deeply before starting the exam and throughout the test. This helps reduce anxiety and improves your focus and concentration. Preparation is key to feeling confident. Familiarize yourself with the test format and the types of questions you can expect. Reviewing the practice tests can offer a solid understanding of what to anticipate and help reinforce your knowledge in areas where you may need additional focus. Make sure you have a solid understanding of the fundamental concepts. Review basic electrical theory, including Ohm's law, which states that voltage equals current times resistance, written as voltage equals amps times ohms. Understanding this relationship is fundamental to solving many electrical problems. Kirchhoff's law should be known, including Kirchhoff's current law, which states that the total current entering a junction must equal the total current leaving the junction, and Kirchhoff's voltage law, which states that the sum of the voltages around any closed loop in a circuit must equal zero. These laws are essential for analyzing complex circuits. Calculations involving power, voltage, current, and resistance are essential. Remember that power equals voltage times current, power equals current squared times resistance, and power equals voltage squared divided by resistance. These formulas are crucial for determining the power consumption and requirements of electrical systems. Understand single-phase and three-phase power systems. Learn how to calculate voltage, current, and power in both types of systems. Be familiar with the different configurations such as delta and Y connections, and their respective voltage and current relationships. Motor calculations, including full load current, starting current, and conductor sizing, are important. Understand the National Electrical Code requirements for motor installations and protection. Learn how to calculate the appropriate conductor sizes and overcurrent protection for different types of motors. Transformer calculations, including voltage ratios, current ratios, and power ratings, are necessary. Know how to determine the appropriate transformer size for various applications and how to calculate voltage and current transformations. Conductor sizing is crucial for safe and efficient electrical installations. Understand how to use the National Electrical Code tables to determine the correct conductor size based on ampacity, temperature rating, and other factors. Conduit sizing involves calculating the appropriate size of conduit to accommodate the required number of conductors. Be familiar with the National Electrical Code tables for conduit fill and understand how to apply the directing factors for multiple conductors in a raceway. Overcurrent protection, including fuses and circuit breakers, is essential for protecting electrical systems from overloads and short circuits. Understand how to select the appropriate overcurrent protection device based on the conductor ampacity and the equipment being protected. Grounding and bonding are critical for safety. Understand the difference between grounding and bonding and how they protect against electrical shock and fire hazards. Be familiar with the National Electrical Code requirements for grounding and bonding electrical systems and equipment. National Electrical Code Article 250 covers grounding and bonding. Equipment grounding ensures that non-current carrying metal parts of electrical equipment are grounded, providing a low impedance path for fault current to return to the source. Bonding connects these metal parts to create an electrically conductive path, ensuring that they are at the same electrical potential. Ground fault circuit interrupters, or GFCIs, protect people from electric shock by detecting ground faults and quickly interrupting the circuit. Know when and where GFCIs are required by the National Electrical Code, such as in bathrooms, kitchens, and outdoor locations. Arc fault circuit interrupters, or FSIs, protect against fires caused by arcing faults. Understand when and where FSIs are required by the National Electrical Code, typically in dwelling units, specifically in branch circuits that supply outlets or devices installed in dwelling units. National Electrical Code Article 210 covers branch circuits. Branch circuits supply power to various loads, such as lighting, receptacles, and appliances. Understand the different types of branch circuits, including 15 amp, 20 amp, and 30 amp circuits, and their respective uses. National Electrical Code Article 220 covers branch circuit, feeder, and service calculations. Load calculations are essential for determining the required capacity of electrical systems. Learn how to calculate the demand load for various types of occupancies and equipment, including lighting, receptacles, and appliances. Voltage drop calculations are important for ensuring that voltage at the load remains within acceptable limits. Understand how to calculate voltage drop based on conductor size, length, and current, and how to select conductors that minimize voltage drop. National Electrical Code Article 300 covers wiring methods. Wiring methods describe the different ways that conductors can be installed, such as in conduit, cable, or raceway. Be familiar with the various wiring methods and their respective requirements. National Electrical Code Chapter 4 covers equipment for general use. This chapter covers the installation and use of various types of electrical equipment, such as luminaires, appliances, and motors. Be familiar with the requirements for each type of equipment. National Electrical Code Chapter 5 covers special occupancies. This chapter covers the installation and use of electrical equipment in special occupancies, such as hazardous locations, healthcare facilities, and swimming pools. Be familiar with the specific requirements for each type of occupancy. National Electrical Code Chapter 6 covers special equipment. This chapter covers the installation and use of special equipment, such as electric signs, elevators, and welders. Be familiar with the requirements for each type of equipment. National Electrical Code Chapter 7 covers special conditions. This chapter covers the installation and use of electrical equipment under special conditions such as emergency systems, fire alarm systems, and critical operations power systems. Be familiar with the requirements for each type of condition. National Electrical Code Chapter 8 covers communication systems. This chapter covers the installation and use of communication systems such as telephone, data, and cable television systems. Be familiar with the requirements for each type of system. National Electrical Code Chapter 9 contains tables. This chapter contains tables that are used for various calculations such as conductor ampacity, conduit fill, and voltage drop. Be familiar with how to use these tables. Specific code articles to review include Article 210 for branch circuits, Article 213 for feeders, Article 220 for load calculations, Article 230 for services, Article 250 for grounding and bonding, Article 300 for wiring methods, Article 310 for conductors, Article 314 for junction boxes, outlet boxes, device boxes, and pull boxes, Article 400 for flexible cords and cables, Article 404 for switches, Article 406 for receptacles, Article 408 for switchboards and panel boards, Article 430 for motors, Article 440 for air conditioning and refrigeration equipment, Article 450 for transformers, Article 500 for hazardous locations, Article 517 for healthcare facilities, Article 547 for agricultural buildings, Article 600 for electric signs and outline lighting, Article 625 for electric vehicle charging systems, Article 680 for swimming pools, fountains, and similar installations, Article 690 for solar photovoltaic systems, Article 700 for emergency systems, Article 701 for legally required standby systems, Article 702 for optional standby systems, and Article 705 for interconnected electric power production sources. Understanding these articles will provide a solid foundation for the exam. Grounding electrode conductor sizing is crucial for ensuring a safe and effective ground. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Refer to National Electrical Code Table 250.66 to determine the appropriate size of the grounding electrode conductor. Equipment grounding conductor sizing is based on the overcurrent protective device protecting the circuit. Refer to National Electrical Code Table 250.122 to determine the appropriate size of the equipment grounding conductor. Bonding jumper sizing is essential for maintaining a low impedance path for fault current. The size of the bonding jumper is based on the size of the largest ungrounded conductor. Refer to National Electrical Code 250.102. Understanding how to size these conductors is critical for safety and compliance. Conduit fill calculations are necessary to ensure that conduits are not overfilled with conductors. The National Electrical Code specifies the maximum allowable fill for different types of conduits. Refer to National Electrical Code Chapter 9, Table 1 for conduit fill percentages. Conductor directing factors are applied when multiple current-carrying conductors are installed in a raceway or cable. These factors reduce the ampacity of the conductors to prevent overheating. Refer to National Electrical Code Table 310.15 to determine the appropriate directing factors. Box fill calculations are necessary to ensure that electrical boxes are not overfilled with conductors, devices, and fittings. The National Electrical Code specifies the maximum allowable number of conductors, devices, and fittings that can be installed in a box. Refer to National Electrical Code 314.16 to determine the box fill requirements. Motor full load current is the current a motor draws when operating at its rated horsepower and voltage. The National Electrical Code provides tables that list the full load currents for different types of motors. Refer to National Electrical Code Tables 430.247, 430.248, 430.249, and 430.250. Motor overload protection is required to protect motors from overheating due to overloads. Overload protection can be provided by thermal overload relays, fuses, or circuit breakers. The National Electrical Code specifies the maximum allowable size of the overload protection device. Refer to National Electrical Code 430.32. Motor short circuit and ground fault protection is required to protect motors from short circuits and ground faults. Short circuit and ground fault protection can be provided by fuses or circuit breakers. The National Electrical Code specifies the maximum allowable size of the short circuit and ground fault protection device. Refer to National Electrical Code 430.52. Transformer primary and secondary currents are related by the transformer's voltage ratio. The primary current is equal to the secondary current multiplied by the voltage ratio. Understanding this relationship is essential for calculating transformer currents. Transformer overcurrent protection is required to protect transformers from overloads and short circuits. The National Electrical Code specifies the maximum allowable size of the overcurrent protection device. Refer to National Electrical Code 450.3. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Voltage drop can cause equipment to operate inefficiently or fail. The National Electrical Code recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Refer to National Electrical Code 210.19a on FBN number 4 and 215.2 AFI FBN number 2. Demand factors are used to reduce the calculated load for certain types of occupancies and equipment. Demand factors are based on the assumption that not all loads will be operating at the same time. The National Electrical Code provides demand factors for various types of loads. Refer to National Electrical Code Article 220. Neutral load calculations are necessary to determine the size of the neutral conductor for a service or feeder. The neutral conductor carries the unbalanced current in a 3-wire or 5-wire system. The National Electrical Code specifies the requirements for neutral load calculations. Refer to National Electrical Code 220.61. Harmonics are distortions of the sinusoidal voltage and current waveforms. Harmonics can cause equipment to overheat and malfunction. Understanding the causes and effects of harmonics is important for maintaining a safe and efficient electrical system. Power factor is the ratio of real power to apparent power. A low power factor can cause equipment to operate inefficiently and increase energy costs. Understanding how to improve power factor is important for optimizing electrical system performance. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning, switching, and other events. The National Electrical Code specifies the requirements for the installation of surge protection devices. Refer to National Electrical Code Article 280. Emergency systems are designed to provide power to essential loads during a power outage. The National Electrical Code specifies the requirements for emergency systems. Refer to National Electrical Code Article 700. Standby systems are designed to provide power to non-essential loads during a power outage. The National Electrical Code specifies the requirements for standby systems. Refer to National Electrical Code Articles 701 and 702. Fire alarm systems are designed to detect and alert occupants to a fire. The National Electrical Code specifies the requirements for fire alarm systems. Refer to National Electrical Code Article 760. Understanding these fundamental concepts and National Electrical Code requirements will significantly improve your chances of success.